Welcome to this video. We're going to be talking about transitive closure and the Floyd-Warshall algorithm in graph theory. Let's start this video off with a quick review of what a graph is, and it looks something like this. You can see that we have a lot of vertices and we have edges connecting those vertices. Some vertices are connected by an edge, whereas other vertices don't have an edge between them. To explain transitive closure, I'm first going to explain what transitive means. You may remember that a transitive property looks something like this. If we have three variables a, b, and c, and we know that if a is greater than b and b is greater than c, then by the transitivity property, we know that a is also greater than c. This can also be visualized. So if we take a here, noted by this circle, and we have this relationship with b, and b has a relationship with c, then we can also draw an arrow representing a relationship between a and c. So in graphs, we can do something very similar. Let's take for an example the vertices a, b, and c in this graph here. So by the transitivity property, since we see that there is an edge between a and b, and we see that there's also another edge between b and c, but there's no edge between a and c, then what we can do by the transitivity property is to draw an edge between a and c. That is the basics of transitive closure. Transitive closure of a graph is finding all sets of vertices that have this property. Let's take a look at the formal definition of transitive closure. The transitive closure of graph G is a directed graph G star such that the vertices of G star are the same as the vertices of G, and G star has an edge UV whenever G has a directed path from U to V. So that's exactly what we just saw in the previous slides. Let's take our original graph and call this graph G. If we want to find G star of G, then what we have to do is go through each and every vertex and draw out its transitive closure. So, for an example, we have the vertices A, B, and D. There are edges between A and B and D, so we can also draw an edge between A and D by the transitive property. We can do the same for A and C, B and H, and A and G. Now that we've found all of the transitive closures of all the vertices, we can call this graph G star. So that's a visual of what we're looking at. Let's take a look at how to program this through the Floyd-Warshall algorithm. Alright, so I've created a very basic adjacency list graph data structure here that we're going to work with. This data structure contains three properties. The first property is the count for the number of vertices here. Our second property is a list of arrays, or an array of lists, I should say. The list represents an array of all of our vertices, and within each of those arrays, there's another list that contains all of the vertices that vertex is connected to. The third property is a directed property, which is a Boolean. This tells us whether or not the adjacency list graph is a directed graph or not. I've got a constructor that initializes all of those properties above, and I have an add edge method that allows us to add edges between two given vertices. I've also got another method here that allows us to retrieve the edge between two vertices as well. In my main method, I have a lot of code here, and that's because I've added the functionality to draw on the screen. So we'll be able to see what the graph looks like when we run the program here by painting it onto a canvas. So what I've got here is I've instantiated our adjacency list graph with 6 vertices. This will be similar to the graph that we saw in the presentation. I've added all of the edges that we saw earlier as well, and I call my draw graph method that allows us to see this drawn on the screen. So let's run this and see what our graph looks like. Perfect. So you can see that we have all of our 6 vertices, and we have edges between some of the vertices, and some of them don't have edges as well. Now, if I run the transitivity closure on this graph, here's a sneak peek of what it will look like. There we go. So we can see that we have 4 additional edges that are highlighted in red, and those are all the transitive closures of the vertexes from the source to the destination. Let's take a look at what the algorithm looks like now. So inside of our adjacency list graph data structure, I've added in an extra method here that will allow us to add edges to any adjacency list graph. So to start with, I've made this method static so that we can call it without having to instantiate our object, and it takes in an adjacency list graph object G. What this algorithm does is it loops through all of the vertices 3 times and checks to see if we have that A, B, B, C pattern. Let me explain. The first loop that we have here goes through all of the vertices once. We have another loop that goes through all the vertices again. This allows us to check each k vertice with each I vertice. Note that at one point during the loop, I and k will be the same value, and this means that we will be checking the same vertices. We don't want that to happen, so we add this condition I is not equal to k here. Next, we also check to see if that there is an edge that exists between I and k. If it does, then great. Let's move on with the algorithm. If we do see an edge that exists, we're going to loop through all of the vertices one more time. This time, we're again going to make sure that we are not checking our own vertice here. That's why we have I is not equal to j and j is not equal to k. The other condition here is to check whether there is an edge between k and j. Now earlier, we checked to see if there's an edge between I and k here. So if there's an edge between I and k, and there is an edge between k and j, then we can apply the transitive property that we've discussed earlier. Lastly, we finally check to see if that there is an edge that does not exist between I and j. If it does not exist, we should add an edge because of the transitive property between I and k and j. And that's the algorithm in the works. This can be particularly useful when you're dealing with a very large graph with lots of vertices and lots of edges. Let me give you an example of what this might look like. So what we've got here is a little bit of a bigger graph with a little bit more edges. So you can see that it already kind of looks a bit of a mess, and when we calculate the transitive closure, we're going to see a lot more lines than before. So let's set the property to true so we can see what the transitive closure looks like. And as you can see, we have a lot more red edges on our graph now. One quick thing to note about this algorithm is that it actually runs in a time complexity of n cubed. This isn't exactly the most efficient algorithm, but you can see how the bigger the input size is, the longer this algorithm will take to run. This is because we're looping through all of the vertices 3 times in order to add all of the transitive edges. So that's it for this video. I hope you guys learned something new today. Thank you for watching.